All right, algebra students, today we are talking about exponential functions and the rule of 4. And we're going to consider this using the Frere model. If you're not familiar with the Frere model, it's a way of thinking about new vocabulary. So it fits sort of nicely with the rule of 4. So here's what we're going to do. We're going to take a piece of paper. So pause the video and go get a piece of paper. It doesn't matter what kind it is. It can be lined paper, it can be printer paper, it can be scratch paper, whatever you have on hand. We're going to take this piece of paper and we're going to fold it hamburger style. I always fold my paper, my hamburgers. All right, so now we have it folded in half, and then we're going to fold it again. So now our paper is folded in quarters, which is sort of an interesting exponential function in and of itself. Now, you'll notice that we have 2 folded edges and 1 folded edge, and the place where these 2 folded edges and the 1 fold edge meet, you get a very pointy piece. You want to be careful, don't poke your finger. Just kidding. Well, don't poke your finger anyway, but it's not that pointy. Then what we're going to do is fold it down, doggy ear it. So when we unfold it, what happens is we have 4 sections and a little rhombus here. If you folded it and your folds are on the outside edge, no worries, just pause the video, refold it so you get your fold right here in the middle. Now we are going to talk today about exponential functions. So now that your paper is all folded, you are going to write this down. Exponential functions. We're going to first talk about this in the general sense, and then you guys are going to get a little bit of information and you're going to have to decode the other pieces. Now, remember that the rule of 4 tells us that any function can be expressed in 4 ways. It can be expressed as an equation, a table of values, a graph, and what's that last one? A written description. Pause the video so you get that all written down. Now, if we were to talk about the equation, the general form of an exponential function, we would probably say, well, that is going to be y equals a times b to the x power. Now, before we say it, what does a represent? And what is b? A is the initial amount. It's the amount that we start with. When x is 0, any number to the 0 power is 1. 1 times any number is that number. So when x is 0, y is a. And b is that number you're constantly multiplying by. So b is the growth factor. That's the number that's being multiplied. Now, we started with the equation, but we could really start anywhere. Next, I'm going to go to the table because that feels natural to me. But if you're thinking about the graph, maybe you were thinking to go there next. Doesn't matter. All right. Now, when we think about a table of values, we have our inputs x and our outputs y. And we have a whole bunch of numbers. And we could do as many as we like. There. Now, if we start at x equals 0, and I'm going to put that sort of in the middle of the table, even though we're thinking of it as our initial amount, when x is 0, y is a. That's our initial amount. And since our equation is multiplying by b every single time to move over 1, When x is 1, we're going to have a times b. And when x is 2, we're going to have a times b, or a times b squared. And when x is 3, we're going to multiply it by b again to get to the next value. So we'll have a times b cubed. And if we were to move backwards in the table, if we were going to go to back 1, we would do some division, right? Because the inverse of multiplication is division. So we would have a divided by b. Another way to think of this, well, we'll get there another time. And if we were to go back again, we'd have a divided by b squared, right? Because b squared, a divided by b squared times b is a over b. And multiply by b again, we get a. And so it fits our pattern. Okay. Now, if I'm going too fast, you can just pause the video or rewatch it to catch up. Now we're going to consider the graph. Remember that these are our x values and that's our y-axis. So all right, now we're going to kind of speak in the general form, so it'll be interesting. Let's see. If I have here this point right here, that's our initial amount, right? When x is 0, I go over 0. I'm going to go up a. So in general, I would write this as 0, a. And then our next point is going to be over 1. So we're doing that growth factor one time. So over here, some amount is going to be 1a times b. Now, part of the pattern about exponential functions is that they grow really quickly. So our next one, over here at 2, will be maybe way up here, a times b or a times b squared. So there's a little bit of growth here, but then there's like a lot of growth here, and the next one's going to be even higher and even higher. So when we connect those points, we get a curve whose slope is increasing. The rate of change is getting quicker and quicker and quicker. And then, but as we go back here, it's getting less steep. This would be negative 1a over b. And so what happens is we get this tail for our exponential function where it just seems to kind of flatten out. And we talked about the funny name for that. There's a line at y equals 0 where that graph is approaching it, right? It seems to almost touch. It's getting very, very close. For all intents and purposes, it's touching, but it actually isn't. It's just very, 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 very close to 0. And we call a line that a graph approaches an asymptote. It's a very silly word, and I only mention it because it's fun to say asymptote. All right, now there's a lot we can do with the written description. For example, I could ask you to describe this graph. You might say it grows very quickly on one side and it approaches an asymptote on another. I might have you describe what the initial amount is or what the growth factor is. I might have you describe what's happening in the table. But there's another thing that we could do. We could think about where we see exponential functions in the real world. And we see them in a couple of places. Where do we see exponential growth? Well, we see exponential growth. One example that we're living is with infectious diseases. One of the reasons why we need to stay home and make sure that we're safe from COVID is because at first, we see slow growth, but then all of a sudden, when more people get sick, they infect more people, and we get this very scary curve like that. And if you look at some of our COVID data, you can notice that curve right there. Okay, so infectious diseases, another one where we see exponential growth is population growth. We also see if we put our money in savings, we'll see this kind of growth with compound interest. Now, compound interest can work for you or against you. Compound interest, if you have your money in a savings account, it's working for you. If you have credit card debt, it's working against you. We'll also look at exponential decay this week, and we'll see some examples where exponential decay occurs, like how water cools. I mean, hey, that's fun, right? Or how things of value depreciates, like a car. So I think this video is long enough, but this is really everything that we've learned in the last 3 weeks. So we're going to look at some example problems next, but I'm going to start that with a new video. So just to summarize, exponential functions and the rule of 4. We can think about exponential functions as an equation where y equals a times b to the x. A is the initial amount and b is the growth factor. We can see exponential functions modeled in a table where we keep multiplying by that growth factor. We can see it modeled in a graph with a shape that someone described as sort of like half a U, right? It kind of has a U on this side and like a flat line on that side. And then we actually live exponential functions. We see them with all kinds of examples where things grow really slowly at first and then really quickly. We'll also see it in exponential decay, but that's going to come later this week.